Welcome to the training video anesthesia technology developed by Zaniplan in cooperation with PT Surgica. This video forms part of a series of multimedia applications especially designed for the training of biomedical technicians. The information provided in this video is divided into the chapters: Anesthesia Principles, the Anesthesia Machine, Control Elements, Test Procedures, and Maintenance Issues. It does not refer to a specific model and should only be considered as a general introduction for the function, the use, and the maintenance of an anesthesia unit. Anesthesia Principles. Anesthesia is described as the loss of sensation to the entire or any part of the human body. It might be induced by drugs in liquid or gaseous form, which depresses the activity of the nervous tissue locally, regionally, or within the central nervous system. The latter, also called general anesthesia, has as goal to make and keep a person completely unconscious, meaning asleep during the operation, with no sensations, pain, awareness, or memory of the surgery. The administration of general anesthesia by means of inhaling gases or vapors by breathing into a tube requires an anesthesia machine. The elementary components of an anesthesia machine consists of high-pressure manometers, pressure reducers, measuring tubes, also called rotameters, and a vaporizer. Rotameters. A rotameter is an instrument consisting of a tapered vertical glass tube in which a small float, also called suspended body, is forced upward until its weight balances the flow force. The name rotameter derives from the fact that the float, while suspended, also rotates on its own axis. Every rotameter is calibrated to a specific gas. Please take note about the appropriate reading line of the different floating types. Rotameters used on anesthesia machines usually consist of two glass tubes, one on the left for precision readings from 0 to 1, and a second on the right with a reading range from 1 to 10. Vaporizers. Key element of the anesthesia machine is the vaporizer. Its function is to add the volatile anesthetic to the respiratory air, also called tidal air. Factors which are influencing the function of the vaporizer are temperature, tidal air flow, and the quantity of anesthetics. Nowadays, there are two types of vaporizers in use: draw-over vaporizers and bubble-through vaporizer. The present graphic depicts a draw-over vaporizer. This vaporizer has two paths for the air-respective gas flow. In the dosage path, the gas is flowing over the volatile anesthetic and saturated with its steam. The other path is used as a bypass, where the unsaturated gas flows through. The dose and respective concentration itself is controlled with the help of two metering valves. Another often used vaporizer is the so-called bubble-through type, shown in the present graphic. The airflow in this case is directed through the fluid of anesthetic and therein saturated. The concentration of the anesthetic in this case is controlled with the help of one metering valve. Modern anesthesia machines are provided with temperature and flow compensation, leaving to the anesthetist the control over the concentration of the anesthetic. Classification of anesthesia systems. The present graphic shows a half-open system. It does not contain a rebreathing valve, and its fresh gas flow is equal or greater than the respiratory minute volume. The second system allows the use of T-pieces with high fresh gas flow, meaning 3 times the respiratory minute volume, or T-pieces with low fresh gas flow, namely less than 3 times the respiratory minute volume. The third system in our presentation, called McGill system, allows, like the aforementioned example, the selection between high and low gas option with the same respiratory minute volume characteristics. The fourth system, called to and fro system, may be used as a half-open, non-rebreathing system or as a circle system, whether for medium or low fresh gas flow, meaning a flow slightly over or equal the uptake. The last example in our presentation refers also to the so-called circle system and may be used as a half-open or half-closed system with low or medium respiratory minute volume characteristics. A third option is the use as a closed full rebreathing system, where the fresh gas flow equals the uptake. Circular system. Our next graphic depicts a schematic view of a workstation connected to a half-closed circular system. This type of arrangement allows a time-controlled artificial respiration suitable for multiple applications. One of the applications is the use of assisted respiration, with the possibility to select between an expiratory end respiration pressure of 0 millibar, abbreviated ZEEP, or a positive or negative expiratory end respiration pressure, abbreviated PEEP, respective NEEP. The anesthesia machine. The principles of operation described in the first section of this presentation are valid in general for all anesthesia machines, despite of their appearance or design, which varies from manufacturer to manufacturer and from model to model. The following section demonstrates on a real model the different components of a standard anesthesia machine, their functions, and ways to operate. Control elements. The basic components are the volume control console, the vaporizer, the manometer console, the oxygen monitor, the ventilator control, and the patient circuit with carbon dioxide absorber. Volume control console. The present picture shows the volume control console consisting of a pair of rotometers for oxygen, one single rotometer for compressed air, and a third rotometer for the nitrous oxide supply, comprised also of 2 glass tubes. The gas flow is controlled by turning clockwise or counterclockwise the correspondent metering valves. Beneath the volume controls, we see the cylinder selector, including one alarm marker monitoring the cylinder content. Vaporizers. As already indicated, the key component of the anesthesia machine is the vaporizer. There are as many different models as there are different anesthesia machines. Each vaporizer is agent-specific and calibrated for a single gas. Regarding filling a vaporizer, there are two types, namely funnel or keyed filler types. The latter one decreases the likelihood of filling the vaporizer with the wrong agent. The 5 manometers installed in this anesthesia machine are designed to monitor the existing pressure in the oxygen cylinder, the pressure coming from the hospital's central oxygen supply, compressed air, the existing pressure in the nitrous oxide cylinder, and the pressure coming from the hospital's central nitrous oxide supply. Depending on the configuration, some of the manometers may be optional. Oxygen monitor. Principal element of the oxygen monitor is the LCD display, which indicates the oxygen concentration within the breathing system. Further elements are the adjustment controls, calibrate, level, set, and low volume alarm. The oxygen sensor itself is plugged in its respective connector and attached to the breathing system as indicated. Ventilator control. Advanced anesthesia machines are nowadays fitted out with ventilators allowing a wider range of applications. The ventilator integrated in the present anesthesia machine is operated by means of this control console. The control elements are tidal volume control, inhale-exhale ratio control, peak pressure limit control, respiration rate control and its respective LED display, alarm silence button, pressure display in form of an LED bar graph. Carbon dioxide absorber. Important part of a half-closed or fully closed patient breathing system is the carbon dioxide absorber with its absorbent agent lime soda. Actually, two types of absorbers are in use, disposable and reusable types. The advantage of reusable containers is clearly the reduction of operating costs. The absorbent agent lime soda has to be changed once its color changed from white to red. Test procedures. The following recommended test procedure should be carried out at the beginning of the working cycle or whenever the machine has been moved or serviced. The procedures are considered in general and may vary depending on the equipment configuration. It is essential to consult and follow the instructions of your particular user and service manual in order to assure the proper and safe operation of the equipment. Verify that the machine is connected to a live, grounded outlet. Check for pipeline supplies of 50 to 55 pounds per square inch. Disconnect pipeline supplies. Purge fresh gas from system. Open gas cylinders. Confirm that oxygen and air is greater than 1,000 pounds per square inch and nitrous oxide greater than 600 pounds per square inch. Close cylinders. Confirm no prominent decrease in gas pressure. Reconnect gases to pipelines. Turn on gas to confirm smooth movements of oxygen and nitrous rotometers. Turn off oxygen flows to confirm nitrous flows also decreases, approximately 4 to 1 for nitrous to oxygen. Confirm all rotometers off. Press oxygen flush to verify proper function. Confirm oxygen sensor increases to 90 to 100% oxygen with oxygen flush. Turn on anesthesia machine. If applicable, follow system and ventilator self-test. Check for secure connections of all hoses, fresh gas, pressure sensor, oxygen sensor, and flow sensor. Confirm sample line is securely connected to Y-piece and water trap. Confirm sample line is free of kinks, moisture, and water trap is not filled to maximum. Verify carbon dioxide absorber is filled with fresh absorbent. Remove oxygen sensor from inspiratory valve dome. Press oxygen cal button on monitor. When 21% oxygen is reported, replace sensor onto inspiratory valve dome. Verify sufficient anesthetic in vaporizers. Fill and drain valves are closed. Confirm vaporizer interlock system only allows one vaporizer to be used at one time. Place second reservoir bag on end of breathing circuit. Set ventilator to manual spontaneous. Set APL to 30 centimeters hydrogen oxide on manual increase fresh gas flows or oxygen flush to pressurized system to 30 centimeters hydrogen oxide. Confirm system does not increase beyond 30 centimeters hydrogen oxide. Attempt to manually ventilate second bag. Confirm proper function of inspiratory and expiratory one-way valves. Change APL to spontaneous. Confirm decreased pressure in circuit and inability to generate pressure in circuit. After finishing the test and calibration procedures, set and check the equipment to its final position. Vaporizer off. APL valve open. Selector switch in bag mode. All rotometers at 0 or minimum. Patient suction level adequate. Breathing system ready to use. Maintenance. Although maintenance refers usually to some repair or calibration procedures carried out by maintenance technicians, it starts actually with the proper care of the equipment after its use, namely with the cleaning at the end of each day carried out by the user, following at all times institutional standards. When cleaning the apparatus, great care must be taken to prevent liquid entering components. Clean the following surfaces: painted surfaces, anodized aluminum surfaces, plastic components of the apparatus, clear plastic surfaces, flow meter panel, The exterior surfaces may be cleaned with dampened, lint-free cloth. One of the cleaning solutions listed below should be used. Dilute the cleaning solution in accordance with the manufacturer's instructions. Wring excess liquid from the cloth. Do not drip any liquid into open vents, plugs, or connectors. Dry the surfaces with a cloth or paper towel. Medical-grade impregnated disinfectant wipes containing isopropanol and a disinfectant solution may be used. Special attention should be paid to cleaning the flow meter knobs, the on-off switch, and the oxygen flush, as these are most frequently handled by the anesthetist. Solutions suitable for cleaning: water, diluted mild neutral soap. Solutions suitable for low-level disinfection: diluted non-aldehyde surface disinfectant cleaner, diluted bleach solutions based on sodium hypochlorite or dichloroisocyanurate, diluted chlorohexidine medical disinfectant solution. Please note, it is the sole responsibility of the user to validate any deviation from the manufacturer's prescribed cleaning and disinfection instructions as to efficiency and appropriateness. Preventive routine maintenance. Every 6 months. Visual inspection of the apparatus and its included accessories to check for evidence of damage to external components. Mechanical inspection to ensure the correct physical operation of all connectors and controls. Electrical inspection to ensure safety of main power lead, plug, and all socket outlets. Replace parts, for example, seals, gas cylinder yokes, and manifold seals. Carry out full operational check and make adjustments as necessary according to the manufacturer's checklist. Setting to work and pressurizing the apparatus. Checking contents and pressure gauges. Testing operation of flow control valves. Checking flow tubes and floats. Testing ratio system. Testing control and safety system. Testing pressure relief valves. Checking output at fresh gas outlet, oxygen flush, and auxiliary outlets. Checking operation of electrical system and testing earth continuity of apparatus. Checking operation of oxygen monitor as built into the mobile apparatus. Testing includes accessories for correct and safe operation, for example, absorbers, vaporizers. Check output of pressure regulators and adjust as necessary. Carry out apparatus leak test according to the manufacturer's checklist. Carry out electrical earth continuity test. Carry out full functional test of apparatus including accessories according to the manufacturer's checklist. Once a year, gas supply system. Renew cylinder yoke seals and gas manifold filters. Renew flow meter control valve seals, flow meter filters, and seals. Renew seals and wire springs on bag bar. Carry out full operational check according to the manufacturer's checklist. Carry out apparatus leak test according to the manufacturer's checklist. Carry out electrical earth continuity test. Full functional test of apparatus including accessories according to the manufacturer's checklist.